Hi everyone, this is Nitya Jaikumar, Professor in the Department of Information Technology at K.S.Rangasamy College of Technology. The topic for discussion is combinational logic circuit. So the logic circuit for any digital system may be either combinational or sequential. So this is a broad classification of any digital systems. So in case of combination logic circuit, it consists of only the logic gates where the output at any instant of time will depend only on the present combination of inputs. That is, whatever inputs you give to that digital circuit at the current instant, that only decides your outputs. So this circuit design can be done by means of a set of a Boolean functions which define what the logic the circuit has to be implemented. So here this is a block diagram which shows a combination logic circuit where it is having n inputs and m outputs. N can be any value and similarly m can be any value. So the relation between the input and output can be specified by a truth table. So for the given set of inputs, what may be the output? So that is clearly defined in the input truth tables. So similarly, for each Boolean output, that is M, we have a Boolean function. So referring that Boolean function, the circuit will be designed. So for a combination circuit to be designed, there are a sequence of steps to be proceeded. So what are the design procedure to be followed to design a combination logic circuit? First one, you have to specify what is a design objective, what is a task or what is the objective your circuit has to perform. So that is a specification of the design objective. And then for that objective to be met, what is the required number of inputs and what is the required number of outputs. Then assign a symbol to each input and output variable. So after assigning the symbol, you form a truth table which relates the relationship between the input and outputs. So once a truth table is formed, you can define a Boolean function for each of the output variable, either by using a simplification methods like Boolean algebra or design using a K-map. So whichever is comfortable, we can design it. But see to that the expression what you got for the Boolean function to be reduced, so that once you have a reduced Boolean function, you will have a simplified circuit. So here for analysis, I have taken a design of a combination circuit which is having 3 inputs and 1 output. So the output is 1. Here the condition is given in such a way that the output for the circuit is 1 only when the binary value of the input is lesser than 3. Otherwise the output is 0. So here for the given condition, it is known that it has 3 inputs and 1 output. So X, Y, Z are the inputs and 1 output. We name it as F. So as per the design procedure, we name that we have 3 inputs and 1 output. So since we have 3 inputs, we have all possible combinations, 8 combinations from 0, 0, 0 to 1, 1, 1. And then the output F is designed in such a way that it is equal to 1 when the binary value of the input is lesser than 3. So for these combinations 0, 1, 2 combination which is lesser than 3, the output is 1. For the remaining combination, the output is 0. So whatever the objective is given, that is defined in the truth table. So which relates the input and output. So once the output is defined, you can simplify the truth table by means of a K-map, that is a corner map. We have 3 variables, so draw a 3 variable K-map. Enter the values corresponding for the output in which the combination is 1. So enter the values. So when you observe the K-map, we get a simplified expression like this. We have 2 pairs. This is one pair form. This is another pair form. So we have expression as x bar y bar plus x bar z bar. So for this reduced expression, we have implemented a circuit using 2 AND gates which produces x bar y bar and another AND gate which produces x bar z bar. So we have a reduced expression x bar y bar plus x bar z bar. So the 2 AND gates are given for an OR gate. So the expression was implemented. So this is the way in which you can implement a combination circuits according to your required task. So define the variables and then form a truth table relating the variables. Simplify the truth table using K-map. For the simplified expression, you can draw a circuit. So this circuit can be implemented. Okay, next one. Similarly, the combination circuits can also be used to design an arithmetic circuits. Here, the digital computers that which we use in our day-to-day life are mainly used for implementing variety of arithmetic operations. So the basic arithmetic operation for any function is an addition of 2 binary digits. For example, if we do 0 plus 0, the answer should be 0. 0 plus 1, it should be 1. 1 plus 0, it should be 1. 1 plus 1, the answer should be 1, 0. All these are binary values. So here the circuit which you are going to design for that arithmetic operation, which is an adder, it is also comes under the category of combination logic circuit, because at the current instant, what are the inputs you present, that will decide your output. So the combination circuit that performs the addition of 2 bits is called as a half adder, and that one which performs the addition of 3 bits, that is you added 2 significant bits plus a carry from the previous addition, that is called as a full adder. So here we have 2 inputs and 2 outputs. The 2 outputs are sum and carry. So 2 inputs are the values which are to be added, x and y. Write all combinations 0, 0, 0, 1, 1, 0, 1, 1. We'll have sum and carry. So based on this expression, we have two output variables, sum and carry. So there are two ways for implementing the circuit. One is with just using and OR gates, x y bar plus x bar y, which is the expression for sum, and carry it is x dot y. So because only for this combination the carry is 1. So this is one way of representation. You can also implement using the sum can be the representation of an XOR gate. So just instead of these AND gate and OR gate, you can just replace by an exclusive OR gate, and then carry will be represented by an AND gate. So using a combination circuit design, we can also design an arithmetic circuits. Like this half adder, you can also implement full adder, half subtractor, full subtractor. Likewise, you can implement it. Okay, the next one is code converters, which is the conversion from BCD to XS3 code. So code convert, because there are different types of codes which are available for different digital systems. We may using a system which is following a BCD code, and we may interfacing with some other digital system which is following XS3 code. So we need an interface to do the conversion from BCD to XS3. So like this scenario, we have many cases where you want your code system to be converted to a required form. So all this comes under design of combination circuit. Here the task is to perform a conversion from one code to another code. So whatever your input is, here the input is a BCD. So I have 4 variables A, B, C, D. It is listed from 0 to 9. Actually it is 4 variables 0 to 15. But BCD is valid only from 0 to 9. And for this corresponding BCD, we will be representing the XS3 code, which is from W, X, Y, Z. So for 0, it is 3. For 1, it is 4 likewise, because XS3 code is addition of 3 compared with your BCD code. So in this way, we fill the truth table relating your input BCD and the XS3 code. So once the table is filled up, we can simplify it using the K-map. We have different expression for W, X, Y and Z. So here while filling the K-map, from 0 to 9, the entries are filled. From 10 to 15, it should be filled with X. So what is the X denoted? It is a don't care condition, because it is valid only from 0 to 9. Afterwards, it is denoted as a don't care condition. So by simplifying this K-map, we got an expression for all the output variables. W, this is expression A plus B into C plus D. And then X, this is your expression, and Y, the expression, and Z, it is equal to D bar. So once you got the expression, it is very easy to implement using a combination logic circuit. So this is a circuit we can easily implement, and this circuit is a one which converts a given ABCD, which is here BCD code, to a converted to an XS3 code. So in this video, I have presented you what is a combination logic circuit and what are the design steps to perform a design of a combination logic circuits. Then we have seen 3 different scenarios. One, a given objective is given. Based on the objective, how you design a combination logic circuit. Then we have designed a arithmetic circuit like a half adder. Then we have designed a code converters. So this is a way in which you can design any type of combination logic circuits. Okay, thanks for listening. Happy learning.